So in previous lecture we talked about fatigue failure due to fatigue loading, and we talked about the danger of fatigue loading basically because the failure often happens, okay, even when the stress level is actually at the level below the yielding strength, and it often happens very quickly, very sudden. Okay, so how do we prevent this fatigue failure from happening? Right, so that's a critical job of design here. This is basically where the part of the so-called marine factors come in the picture now. So there are a number of factors that here are used to modify the values that you obtain from lab conditions. So the SE here is endurance limit, and SE prime are the values you obtain from lab conditions. So then what will be the endurance limit in a typical actual environment? So we use this the factors that here to modify it. Each one of the factor corresponding to one condition, and Ka at here corresponding to the surface factor. So if the surface is become it's a rougher surface, then right, how do we calculate the Ka? So this is the formula for Ka to calculate. Okay, the rougher surface it is, the smaller value Ka would be. Kb is a size factor, and this is where we stopped. And lab condition has a size of 0.3 inch diameter. If your actual size of the shaft is more than that or less than that, then we have to use Kb to modify the endurance limit. There are 4 different situations we use the Kb. First situation, when you have a rotating circular shaft under constant loading. So that's the most typical situation. So your Kb formula is listed here. Okay. Now second one is when you have a stationary shaft under reversed torsion. Okay, so that's another situation. We'll use the same formula as the situation number 1. If we have an axial loading, then Kb will just simply set it to 1. If we have a stationary shaft that is subject to reversed bending, so basically a stationary shaft subject to reverse bending, then the Kb here is not a direct application of the formula. It's in the same format, but the diameter DE is not the original diameter of the shaft. The DE here is a so-called equivalent DE. So we derive the DE based on the condition. Basically, if you have a basically non-stationary, we look at the volume above 95% of the maximum bending normal stress, and compared to a rotational shaft, I look at the volume above 95% of this maximum stress. Then you compare the two volume, you will be able to get the equivalent to DE. So for circular shaft, we got the DE is equal to 0.37 D, and for rectangular type of shaft, the DE value is this much here. Okay, yeah. So now let's take a look at the one quick example here, and then we will. Sorry, record. So then we'll continue on the other factors. Okay. Let's look at example. Let's see we have a shaft which looks like this kind of shape. Okay, so here is a shaft. This side here has 38, and this side here has 32. Okay. Yeah. Okay, so we're gonna try to find the Kb, okay, for 2 different scenarios. One is when the shaft is rotating, and the second one here when the shaft is a non-rotating shaft. And we're going to assuming there's a bending at here, okay, applied to the shaft. So if it was a rotating shaft under a bending constant bending at here, or non-rotating shaft subject to reversed bending. Okay, yeah. So the first one here is a simple application for the KB. We're talking about location. Basically, for this particular case, you have to be careful which location we're talking about here, right? So the bigger side is 38 and smaller side is 32. When you have a shaft like this kind of situation, you always use a smaller cross section in here, okay? And that's basically where the critical location is going to be. Okay, so we'll use a D equal to 32 millimeter for the calculation. And then, if you recall the KB, okay, if you look at the KB formula right here, this is your KB formula. So when D is between 0.11 this is an inch. This is an inch at here. Okay, this is an inch. Now, but this question here is in millimeter, right? This is in millimeter here. So here is the formula when you have a millimeter. Okay, so when D is between 2.79 to 51 millimeter, okay, and this is D greater than 51, less than 254 millimeter. Okay. So if the dimension is given in millimeter, then here's your KB formula. So apparently our current key D32 is the first formula, so that's 32 over the 7.62, and then to the power of 107, and this is approximately 0.5858. Okay. This is when your shaft is rotating and constant bending, so that constitutes this completely reversed loading condition here. Okay, yeah, that's your KB. And if the second case, if the same shaft not rotating, but there is a reversed bending, right? Reversed bending, complete reverse bending. Then, according to our formula, we need to calculate this equivalent diameter DE first. So 37 times 32, and this is equal to 11.84 millimeter. Okay. And then we use this same formula for calculating the KB here. So 1184 over 7.62, and that gives us slightly bigger value, actually 0.95954. Okay. So that's a simple example, how you can apply the formula appropriately and to get the size factor KB. Okay, so let's look at the next factor called loading factor. Okay, loading factor here. Loading factor basically, any one of the factor are the purpose is to modify to a different scenario from the lab conditions. When the specimen is subjected to lab conditions here, the lab condition basically the RR Moore rotating machine, and the specimen is subject to what type of bending, what type of loading, bending, right? It's a bending type of loading. So loading factor, let's say the first one, if it's a bending, okay, if it's a bending, then you don't need to change anything, basically just one, because that's the same loading condition as the lab condition, basically. Okay. If the loading condition is axial loading, okay, your KC is 0.85. Okay. If the loading condition is pure torsion, okay, your KC will be 0.59. Okay. So this is basically the results, let's say, from experimental results here. There's another scenario is called combination of this kind of loading. We call it, let's say, combined loading. Okay, so combined loading here. So it could be combined loading, could be basically means it's a combine of bending and plus torsion, or a combine of bending plus axial. Okay, yeah. So for example, as I said, it could be bending plus axial. Okay. So if this is the case, we set our Kc equal to 1. Okay, Kc equal to 1. Okay. The reason actually later when we look at the combined loading condition, okay, combined loading, the type of scenario, we have a separate factor to account for this combined loading condition. So for the factor at here, the marine factor, to correct the endurance limit, then we'll set the Kc, which is simply equal to 1. Okay? Yeah. Okay, so the next factor here is the Kd. This is called the temperature factor. Okay, the Kd here is called temperature factor. So for temperature factor, we use the following table right here for our calculation. So this table is from table 6-4. So this is a table 6-4. And this is your first method. There's another method using formula here. If you look at the 6-4 here, basically there is a temperature reading at here, which is in the degree, and this side here is temperature in the Fahrenheit at here. Okay, yeah. And the other column here is the ratio of so-called S capital T over S RT. Okay, so the S capital T, this one here, this is the so-called tensile strength at operating temperature. Okay, so this one here refer to tensile strength at operating temperature, and this one here SRT, this is the same concept. It's also tensile strength, but this is at the room temperature. Okay, yeah. So room temperature basically is like 70 Fahrenheit or 20 degree, okay, Celsius. So your Kd is basically these values here. Okay, this is your Kd's here. This is your basically your Kd. Okay. So if given the temperature here, it's just your Kd over there. Sometimes you probably are not exactly given, let's say 150 or 200. You're probably given as 180, for example, right? Yeah. So let's say your operating temperature is 180. Then how do you find the Kd then? Right? So what do you do? So you can use the mathematical approach, which is called interpolation. Okay? So you can interpolate to get this Kd value. Okay? Yeah. So basically interpolate if necessary. Good? Yeah. This is your first approach. You can use the table 6-4 to calculate the Kd, or to find the Kd. Right? There's another approach. Okay, let me call that the second method here. The second method here to use is to using this equation 6-27. Okay, there's the equation 6-27. It's a fairly long equation. I'll just write a portion of that. You can take a look at your textbook. Okay, it's an equation in a format like this. And then there's TF squared. Okay, so it's a fairly long equation here. Okay, there's a lot of decimal numbers and stuff like that. Okay, yeah. So this equation basically you insert the temperature and then you get the Kd. So that's In terms of the a lot of time we use Excel, and this one probably will come in handy, instead of looking at the tables, right? Yeah. But the only catch of this formula is this TF in this formula is in Fahrenheit. Okay. So this is in Fahrenheit only. This is not a degree. You can plug in a Celsius degree value into this formula, so that'll give you completely wrong results. Yeah. Another thing is for this formula applies only to the range between 70 degree to 1,000 degree Fahrenheit here. Okay. So that's it's basically more of a curve result of a curve fading. Okay. Yeah. So that's your KD. And next one is KE, is called reliability factor. Okay. Reliability factor. And this one we use table 6-5 to find the KE value. So this is your table 6-5. In the midterm, it's not open book, but you will be allowed to copy some of the tables into your formula sheet. Okay, yeah, just in case you need that. Sometimes I'll just include some of the table in the exam papers. Okay, yeah. But anyway, so you'll be allowed to incorporate some of the table into the formula sheet. Okay, yeah. By the way, the midterm is next week. Yeah. It's a closed book, but you will be able to use your own formula sheet. Okay. Yeah. So I'll send out another email just detailing the requirements. Okay. And then a calculator is also allowed. So from this table here, there's a reliability on the first column here. There's all different type of reliability. Okay. And your KE value basically is the last column here. Okay, so this last column is your KE value. Okay. There's another column here that we call a transformation variable. If you look at this table here, so your KE is actually also related to that. So this is your ZA, and if you use this formula, and you get your KE too. Okay. Yeah. So same thing. Okay. Okay. So the last formula is called KM. It's miscellaneous formula. Okay. So the miscellaneous formula basically means there are many other conditions that the possibility that you didn't account for, right? Yeah. Then how do we take care of these things? So you can always use an estimated factor KM here to basically account for all the other type of conditions. But in short, in our case, we're going to set our KM to be 1 in all of the most cases over there. Okay. Yeah. So that basically is all the factors for the marine factors that we're talking about right here. Okay. So you have a KA, KB, KC, KD, KE, and KD, KE, right, and then KM. Okay. Yeah. A, B, C, D, E, F. We'll look at an example when we finish the next portion in here, and then together we'll look at an example basically how to given the actual an example, how do we find all the different basically marine factors. Okay. Yeah. So let me continue it here. When we finish this portion, and we'll look at an example, comprehensive example together. Right. Yeah. Right. And as a matter of fact, yeah. Maybe you can pass along this handouts that are here. Okay, so the next topic out of here is basically how do we create the stress life diagram? and we call that SN diagram. Okay. Yeah. If there's leftovers, if you guys could pass over to this side of class. Okay, so there's one question that you should think about is, we're talking about fatigue loading. So one question is, okay, so we design for infinite number of cycles, or we design for finite number of cycles based on certain loading conditions, right? Yeah. The loading condition could be given. Say, okay, so the part is subject to complete reversed loading of 100 ksi, for example, amplitude. Okay, yeah. And then the next question is, how many cycles would it fill, right? Would it fill at a number cycle greater than 10 to the power 6, which is infinite? Or would it fill at a number cycles that's less than a million, right? Maybe a 10 to the power 5 or multiplied by something, okay? Yeah. So that's a question that we should ask. And then how do we find that answer then? This is basically the step. We need to be able to create a stress life diagram. Create a stress life diagram can be from experiment. That's probably the most straightforward method. You do experiment. You manufacture the sample and then put it on our raw material machine, and it's subject to this different loading conditions, different basically stress level, and you can plot out this SN diagram, right, with a whole bunch of data. Okay, but then often in time, the other thing is not necessarily you can have the experimental data all the time. So then what do we do? So if we still need that stress life diagram, then we have to find a way to approximately reconstruct this stress life diagram, okay, using some approximation methods at here. Okay, so here is the typical stress life diagram in here. Okay, so this is basically what we see in the previous lecture. Okay, so let's take a look at for this one here. Remember, for this one here, this is created, okay, with completely reversed loading. So basically means you have a stress like this, okay, and corresponding to a stress amplitude sigma A at here, okay, sigma A. And your mean, this one here, the mean value sigma m is 0, okay, the mean value is simply 0 here. So if I look at this diagram here, an observation is for any values that below this one, which is a 10 to the power 3 approximately, so below 10 to the power 3 we call the low cycle. This portion, okay, this is in log scale already, okay. This portion in here has a fairly small change. So initial SUT, that's, you apply SUT and then it's broken, right? So there's a very small change at here. So then there's a big slope at here, and then there's this knee point, and it becomes horizontal here, right? Yeah. So what we typically interested is the high cycle region. So basically, this region is what we typically interested in here. All right? Yeah. And of course, the knee point here is SE. So we can consider this portion as a flat. And what we try to create SN diagram here is to focus on the high frequency portion, basically from the 10 to the power 3 number cycles, and then up to infinite number cycles over there. Okay? Yeah. So that's what we're going to focus on here. Yeah. So here is the objective. Objective is to create an SN diagram for n greater than 10 to the power of 3, okay, and which we call that high cycle frequency. Okay. And then to create this portion, as you can see, experiment shows up here is in the log-log scale, between this and this point, A and B point, it's basically a straight line. Okay, it can be approximated with a straight line at here. Okay, and this A point at here. So to create a straight line here, we only need 2 points, right? We only need 2 points to create a straight line. The A point has a coordinates 10 to the power 3, and then has another value over here. Okay, this value here. Okay, this value. So this value here, okay, is calculated using the so-called f times SUT. So here is f times SUT here. I'll talk about what f is. And the B point has a coordinates 10 to the power 6, and of course SE at here, right? SE. So if you can find 2 coordinates, then you can just draw a straight line, right? And in the log-log scale, then you'll be able to create this portion of the SM diagram. Okay, yeah. So as long as we have the 2 coordinates, then we're fine. So this B point actually already is 10 to the power 6. SE is the corrected endurance limit, and that we just did it. You know, we have this K8, KB, KA, KB, KC, KD, and KE, right, and KM. So you'll be able to get this SE by applying the marine factor SE prime. So this one here, F at here. This F is called fatigue strength fraction. Okay, fatigue strength fraction. So you will have to look at the figure 6-18. Okay, so figure 6-18 to find this F value at here. SUT is the ultimate strength. Figure 6-18 will give you this fatigue strength fraction, the value of the small f. So this is the figure 6-18 at here, right? 6-18. Based on the given material, so you basically, right, draw horizontally, vertically, horizontally, then to find f at here. Okay, that's how you find f. Now this figure stops at 70. Now if SUT is less than 70 KSI, and you can just simply let the f equal to 0.9. Okay, so that is the small f value at here. Is that good? Yeah. Okay. Now this AB is a straight line here, but that's in the log-log scale. Okay, if it's a not log-log scale, for the mapping between the fatigue strength and the number of cycles is actually this formula. Okay, so SF equal to AN to the power A times N to the power of B give you the fatigue strength here, right? So SF is the fatigue strength. Okay, so basically it's this vertical axis here, fatigue strength. Okay, now if I take a log of both sides here, if we take log both sides, so you get log SF at here equal to, this is log A plus B and log N. So if you take log of both sides of this equation, and you get this one here. Okay, you get this. And this is like basically consider this side here. This is like a y equal to this, and then a constant plus b, and then times x. Okay, it's like this. And this is basically a straight line, right? This is basically a straight line here. Good? Yeah. And this is a line describing the portion between A and B point. Okay, so this between this A and the B point, and that's this line here. Okay, yeah. So what are the A value? What are the B value then? Right. So what we can do is we can just simply plug in the coordinates of the points A and B. Remember that coordinates for A, right? Coordinates for A is 10 to the power 3 F SUT, and the B is 10 to the power 6 SE. Okay, yeah. So we can plug in these coordinates into the two equations, into this equation here, the line equation. Then we can solve for A and solve for the B. Okay, so you'll get the A at here equal to F SUT square over SE, and the B here is equal to negative 1/3 and log F SUT and over SE at here. Okay. So a couple equations, most important equations that are here. So let me make a comment that are here. Number 1, here is SF equal to A times N to the power of B. Okay, N to the power of B. So what this basically means, what is the fatigue strength at this number of cycles? So you plug in a number of cycles here, you get this fatigue strength with the formula A times N to the power of B, and A equal to this and B equal to this. Okay. So that's your first. That could be the first interpretation of this formula here. And the second interpretation is we can also estimate. Okay, estimate the number of cycles to failure, okay, given the amplitude of the completely reversed cycle. Okay. So remember how this graph is obtained, right? This graph basically, you apply this completely reversed loading, okay, or stress to the part, and then you observe how many cycles it'll fail, right? So if you have this sigma A at here, so this side here, this axis, we call that fatigue strength, but it's actually basically the amplitude of this completely reversed loading, right, of stress. So this side here essentially SF, or it's a sigma A, the amplitude right here. Okay. Then the question here is, let's see if we have the sigma A, right? It's like you have the sigma A over here. You know how much amplitude you applied for the complete reversed loading. Then what is the number of cycles, right, corresponding to that loading condition? So that's basically the idea here, to estimate the number of cycles to failure given sigma N, sigma A here. So now what do you do in this case here is you replace this SF with sigma A. Okay. So sigma A equal to A times N to the B. Then you solve for the capital N. So capital N and here. Okay, you solve for that. Then you get the number of cycles to failure. Okay, yeah. So that's two different basically directions how to interpret this single formula, right? Yeah, get the fatigue strength at the number of cycles, or to estimate number of cycles given the amplitude of the complete reversed stress. So let me show you an example right here. Okay, let's say SUT equal to 70 KSI and SE equal to 30 KSI. Okay, so this is corrected already. Okay. And then sigma A equal to 40 KSI. Okay. So, and we wanted to know how many number of cycles will this part fail, right? Subject to this completely reversed loading. So basically here you have the loading here. Okay. Yeah. So simple applications of this given formula. A value equal to F SUT square over SE. Okay. F is the fatigue strength fraction. SUT is 70 KSI, as we see when you have 70 here, and F equal to 0.9. So that's from figure 6-18. So your F equal to 0.9. SUT is given, SE is given. Okay. Then you can calculate the A value, 132.3. And then we can calculate the B value, negative 1/3 log F SUT over SE. Okay. Same thing, plugging all the values here, you get your B value, okay, negative 0.107. So now you can estimate the number of cycles to failure, which is 40. That's your sigma A over the A value, and then 1 over B. So given this one here, okay, yeah, you can do the calculation here. But before we do the calculation here, okay, so let's take a quick look at it here, do a quick estimation even. SE is 30, and sigma A is 40. So what do you think the number, capital N, calculate number of cycles? Will it be less than 10 to the power 6 or greater than 10 to the power 6? The calculation in here. And why? What do you think this value here? Would it be a value less than 10 to the power 6 or greater than 10 to the power 6? Greater than 10 to the power 6 meaning what? If it's greater than 10 to the power 6, means the part has what kind of a life? Infinite, right? Yeah. And if you look at this figure here, the part will only have infinite number of life if the sigma A value is actually what? Below which value? Below this endurance limit, right? If the sigma A value is bigger than SE, somewhere here, then you would not have this infinite number of life. So coming back to this question here, what's SE? 30, and the sigma A is 40. So that immediately will tell you that this part will never have infinite number of life. So the N value calculated must be less than 10 to the power 6, right? So that gives you a rough, basically, things here. If your calculation doesn't make sense, then you got to double check your calculator, basically, okay? As a matter of fact, you know, this is somewhere you have to be careful. I have seen many mistakes in the past. Because of the formula right here, a lot of some of you actually having trouble using the calculator doing this log calculation. Okay, this is a log calculation, not a lawing calculation, right? Yeah. Huh? Yeah. So that basically saying the part will fail at a roughly estimated, okay, at 6 times 8.7 times 10 to the power 6, 10 to the power 4 number of cycles. Okay. Okay. So far, if you think about it, so far what we have been describing, talking about, is all about fatigue failure under complete reversed normal stress, right? Normal stress. Okay. So you have a stress sigma A, okay, completely reversed. So here's a question here. Basically, what do we do essentially? Okay. If we have a part, okay, which is under, let's say, completely reversed torsion. Okay? Or in other words, instead of the sigma A is alternating, it's the tau A is alternating, right? Basically twisting it back and forth. Okay, yeah. Then, how do we make changes at here to reflect this type of loading then, right? Yeah. A number of steps you need to do at here. Okay. So we don't need to redo everything at here. So if you look at the formula here, we have SUT. Then, if it's subject to complete reversed torsion, so we'll replace SUT with SSU. So SUT is the ultimate strength. We'll replace that with ultimate shear strength, SSU. Now, ultimate shear strength, you could look up a table, but if it's not necessary, you have the value for all the SSU. And here's the formula to approximate this SSU value. It's approximately 0.67 times SUT. This is actually from equation 6-54, okay, in the textbook. Okay, so you can take a look at that. At the same time, replace the sigma A with tau A. Okay, so because it's not the normal stress, it's shear stress now. That's your first step here. And then the second step here, okay, the SE, this value here, this is the endurance limit. And when you calculate this endurance limit, okay, now SE here, because the loading is not a bending here, right? Loading is not bending. So when we calculate this SE, if you recall that there is a loading factor Kc, isn't it, right? There's a loading factor Kc. So the Kc needs to use that 0.9 to do this calculation of the SE. Because 0.59, that's the value, okay, for the loading factor when the loading is torsional loading. Okay? Yeah. So after this calculation or replacement, then you can calculate your B value and your A value using this formula now. So here's F SSU, okay, divided by SE, and the A equal to F SSU and divided by SE, and here's the top is the square. And then the N value here is tau A at here divided by A and 1 over A. So that's how you can estimate number of cycles to failure when the part is subjected to complete reversed torsion. Okay? Yeah. Most of the cases we're dealing with is a completely normal stress, but I think one assignment will be this one here. So that's what you need to, the formula you need to use when you have a completely reversed torsion at here. Okay. Okay, so that's the creating SN diagram. This part of the creating SN diagram. This is actually quite useful if you use let's say, for example, if you want to use SolidWorks to do fatigue loading analysis, okay, or stress analysis. Now, in the part when you create that study in the SolidWorks, and you also have to create this SN diagram. Not all material has a SN diagram comes with a library in a commercial software like SolidWorks. So if you choose this material and it doesn't have the SN diagram, then you cannot carry out this fatigue loading analysis. So you have to actually create an SN diagram using the approach that I listed it here. Okay, yeah. So and then you can use the software to do the fatigue analysis. So I have a video there. If you're interested, you can take a look at it. Okay, one of the bonus questions probably on this part in the next assignments. Okay, yeah. Okay, so let's continue from here. Okay, and before we look at an example, there's one more topic at here. Okay, which is fatigue, stress concentration. Fatigue stress concentration factor, Kf or Kf shear, KFS. Okay, so first of all, we use Kf for normal stress, and we use KFS for the shear stress, okay, the substrate. So fatigue stress concentration factor, it has a lot to do with, we learned before the stress concentration factor, right? Yeah. So previously we have a stress concentration factor, for example, sigma mx equal to Kt times the nominal value, or tau max equal to Kts times the nominal value. Right, that's stress concentration factor, Kt, Kts. But these two, if you recall that's basically under static loading condition, right? Static loading. So if you have static loading, then you apply Kt, Kts wherever there is a non-uniform geometry. Okay, whenever there's a hole and there's a notch, okay, and then you can look at the appropriate table or figure to find the Kt value. Okay. So, and now for the fatigue loading here. Okay. Yeah, for the fatigue loading, we have a different calculation. Basically, the notch area, okay, feel this stress concentration differently under fatigue loading, from this static loading here. Okay. So calculation of this fatigue stress concentration factor, Kf, this is the formula for calculating this one here. Okay. Yeah. And in this formula here, the Q is called notch sensitivity. Q is called the notch sensitivity here. Okay. So before we move on to this formula here, I also want to jog you for a very important concept, okay, on the stress concentration factor. When a part is subject to static loading, if the part is a ductile material, do you apply the stress concentration factor or not? Do you remember that discussion, right? If the part is if the part is a ductile material and subjected to a static loading, and the part has a certain hole or notch somewhere, right? Would you apply the stress concentration factor or not? No. Huh? Remember, it's a no. So you only apply the stress concentration factor to what type of material? Brittle. Okay, that's very important. And sometimes it's a testing point, right? Yeah, to confuse you. However, when it comes to the fatigue loading, okay, to the fatigue loading here, doesn't matter whether it's a brittle material or a ductile material. Both of them will feel this stress concentration. Both of them will be equally sensitive to this stress concentration at the notch area. Okay, so the point here is, okay, the differentiation, right? The differentiation is apply fatigue stress concentration factor to both ductile and brittle material. Okay, that's the difference. Okay, if it is fatigue loading and the part has a notch sensitive area, you know, a groove or a hole, okay, make sure you apply this KF or KFS to both of this, to either one of the materials. Okay, and this is basically, it doesn't matter what type of material you're using now. Okay, yeah, just apply it. Okay. So if it's not a normal stress with shear stress, then the formula is basically, okay, it's the same format, just the symbols are different. Okay, so let's call this Q shear. So Q shear and then times KTS and minus 1 right here. Okay. To find this Q or Q shear, okay, to find the Q and the Q shear, so there's a handout that I give it to you, and there's on the second page, actually, there are basically to find the Q or Q shear. Okay, there are two methods. Okay, one is the first method is to use this figure 6-20 or 6-21. Okay, so you use the two figures to find out the Q and the Q shear. So I have the two figures over here. Okay. And this is a figure 6-20, and here is figure 6-21. Okay. The horizontal axis is called a notch radius. So notch radius basically, you know, let's say if you have a bar that gradually change with the radius at a fillet to radius at a here. So this R here, that's basically the notch radius. Or if you have a groove, okay, on the shaft, okay, and that's also the notch radius. All right, yeah. So horizontal axis is the notch radius. Then there are a cluster of curves corresponding to different SUT value. The solid one is steel, and then the dashed one is aluminum. So typically what you do is basically find the notch radius, convert it to inch, and then just go above, and then try to find a corresponding Q value. Okay? Yeah. If your material property is a value other than the value listed over here, then you actually have to do a certain sort of approximation in the game, okay, using this table here, using this figure here. So it's not a very accurate method. Yes. KT is the static stress concentration factor. Yeah. To find a KT, you know, basically we went over the exercise, right? There's appendix A-15- something for various type of loading conditions. Yeah. Then you can find a KT value from there. Okay. So to find this is to find a Q shear, right? A Q or Q shear. So this one here is the Q shear. Okay. So this one here is a Q shear when you have a torsional type of loading. Okay. Yeah. So this is your first method. You can use the figure to find the Q or Q shear. Okay. Now another thing I think we can take a look at again, just to take a look at this maybe KF that here. Okay, this formula. So let's look at some of the extreme cases here. So what happens when Q equal to 1? Right? When Q equal to 1, what does KF equal to? KT, right? KT. Okay? Yeah. So when Q equal to 1, KF equal to KT. So basically it means the parts will feel this stress concentration completely, right? The KT here. Okay? Yeah. Now if Q equal to 0, see that's why it's called a sensitivity, notch sensitivity, right? When Q equal to 1, meaning it's most sensitive, it feels this stress concentration completely. If the Q equal to 0, meaning it doesn't feel anything at all. So if in this case here, KF is actually just equal to 1, right? Yeah. So even though there might be a notch there, for whatever reason, there's actually not feeling this stress concentration. Okay? Yeah. So this one here basically means it's not feeling the stress concentration. Okay. Yeah. And in the two previous figure, okay, it only covers the ferrous material, the steel and the alumina, and the steel and also the non-ferrous aluminum here, right? There's also another type of material you could use, maybe as a cast iron. So in that case, you can use Q equal to 0.2 for all grades of cast iron. Okay, so that's another fact for the Q at here. Okay, so this is your first method using the figure to estimate Q and Q shear. Second method, okay, is to use formula. Okay, use formula for the KF. Okay, formula for the KF or for the Q. Okay, for the Q here. The formula here is this. So let me move this down a little bit here. The formula for the Q is 1 plus root A over root R. Okay, so this is the formula. Yeah. It really doesn't matter whether it's Q or Q shear. Okay. It all takes the same format, but when you calculate the Q shear, that root A will take on a different formula. The root A at here is called Newberg constant. Okay, so this is a root A. It's called a Newberg constant. How do we calculate this root A? It's a fairly long formula. Okay, it's given in my lecture notes, also in the textbook. There are two equations. One is 6-35A. So this 6-35A is for the Q here. Okay, and then this one here is a 6-35B, I believe. Okay, this will be for the Q shear. Okay, this will be the Q shear here. Okay. So there are two formulas for the Newberg constant. If you want to calculate Q, use 6-35A. Otherwise, Q shear 6-35B. I will give you some Excel files, especially Excel files. Solving class examples and tutorial examples, and there will be also templates will be posted later when we do the shaft design. Okay, in those Excel file, there will be the formula basically entered. Okay, for either this Q or Q shear. So they have been tested; they're right. Because this is a fairly tricky one. If you put a one number wrong, then everything is wrong, right? Yeah. So try to recycle that formula in the Excel that I gave it to you. You don't have to re-enter all of this yourself again. Okay? Yeah. So this is basically for using the formula to to calculate Q or Q shear. And then once you got the Q or Q shear, then you plug it in here. Once you get the Newberg constant, you plug in with the notch sensitivity, and then you can get the Q and the Q shear. Okay. Yeah. So and then one more here is one more thing is a comment is that if the given SUT is in megaparsec, so basically these two formula, for these two formula, the SUT value, the units are KSI. So they're not megaparsec, they're KSI here. So you have to be very careful, If your SUT is material, you find the table or the question is in megaparsec, you actually cannot directly use the 6-35A and B formula right away. So we have to, in this case here, we have to modify that Newberg constant formula slightly. For example, for this formula here, right? So what do we do? You will convert this SUT from megaparsec to KSI. So basically, you use this SUT divided by 6.89. So wherever there's SUT, divided by 6.89. Yeah. At the same time, see at the end of the term here, also multiply by square root 25.4. Because 1 inch is 25.4 millimeter, right? Yeah. So if you're given a formula which is megaparsec, the unit, you need to use this formula here for calculating the Newberg constant. And then consequently calculating the the Q and the Q shear. Okay.
So that converts from megapascals to KSI?
Sorry?
So that converts from megapascals?
Yeah, so this is converting from megaparsec to KSI. Yeah. And then, of course, in the end, also convert that from the millimeter to inch, right? Unit. Yeah. So this is square root. That's why there's a square root here. Okay. Okay. Any questions so far? So this is basically all we need for fatigue loading under completely reversed condition. Okay. Yeah. So let's take a look at example here. Okay. And I have a handout to give it to you. Basically the same drawing at here. Okay. So if you look at the examples that I gave it to you here, so I'm going to skip some of the known conditions. So where is my... Yeah, here. Okay. So here's a shaft, basically. It's a rotating shaft, right? If you look at the example, this is a rotating shaft here. Okay. And the force here, basically, this is stationary. And on the two ends of the shaft, there's probably two bearings supporting the shaft at here. Okay. So you have two supporting force from the bearing locations. The stationary force is given 6.8 kilonewton, and it's non-rotating force, right? Yeah. So we're gonna try. What we're trying to do at here is we try to estimate the number of life, basically, or the number of cycles, okay, to failure. Okay, yeah, so that's the question right here. And there are also few working conditions for this question. Okay, there's a number of step locations. So later when we learn shaft, one thing that we're going to learn is the structure of the shaft is a stepped shoulder, okay, stepped shaft. So there's a stepping up, okay, and the shoulder location will be used probably to locate or to fixture certain elements on the shaft accurately. So you may have a gear at this location, right, and here you have a bearing to locate at this location. Okay, at each one of the stepped shoulder here, right, there will be a fillet process at each one of the shoulder, and the fillet has R equal to 3 millimeter radius. Okay. Material is given as AISI 1050 code drawn. It's operating at 450 Fahrenheit, and this is a reliability of 99.99%. Okay. Okay, so with this condition in here, right? So let's just see how we can proceed to find the estimated number of cycles. Okay. For design, actually, the first step, before you jump in here, is to draw the free body diagram, and then draw the bending moment diagram. If there's a torque, also draw the torque diagram. And if there's a shear force, you should also draw the shear force diagram, right? Yeah. So here is the shaft. So we can easily draw the bending moment diagram like this. Okay? Yeah. So of course, here's a free body diagram, and you had to figure out what R1 is and what R2 is, right? You can figure out R1 and R2 easily, okay, by using equilibrium equation, okay, yeah, and then you can draw the bending moment diagram, okay, yeah. Now, once you have the bending moment diagram now, and the next question is, which location should we look at, right? Or which location will be the critical location? Okay, because you're not gonna analyze everywhere, right? You only need to analyze the most critical location. If the most critical location fail 3,000, then you don't need to look at other locations. Other locations, no meaning anymore, right? Okay. So if you take a look at this bending moment diagram here, right? And obviously, it's maximum at this center location, not a center location, at the location where the F force is applied. Okay. And what does bending moment? What type of stress does bending moment cause? Shear. Tension. But what the name of the stress? Stress, what is the shear stress? There's also the other stress was what? The bending normal stress, right? What's going on? So bending moment will cause bending normal stress, okay? And of course we learned when you cut a cross section anywhere, okay, along the shaft, and where is the location maximum at that cross section? Top and the bottom, right? Okay? Yeah. So obviously this is the maximum bending moment. If I just think about the bending normal stress caused by the bending normal stress, then this feel like this is the location that's most critical, isn't it, right? Because that's maximum. However, what other factors that we had to consider in terms of the critical? What are the conditions we have to take into account? What's the nature of the fillet? That's right, fillet will cause what? Stress concentration. So the stress concentration factor is acting as a stress riser, right? Will raise up this stress. So you look at the C and the B location. This is the location with what? With the fillet at the shoulder, right? C location, B location doesn't have the maximum bending moment, but both of them have the stress concentration factor. So that stress concentration factor, if you multiply the stress concentration factor with the bending normal stress caused by the bending moment at these two locations, and chances are they actually will be higher bending normal stress than the location at here. Okay? Yeah. So that's why for this particular question, for this particular shaft, where do you think the critical location would be? B or C? B, right? Yeah, because B has a higher bending moment, and both B and C has the same notch area, okay, notch radius. So B will be the most critical location. So we actually basically will look at, basically this is why we'll only look at the B location. Okay? Yeah. Now you might ask question is this. So you're only considering bending moment, right? With bending normal stress caused by the bending moment. So if I look at the free body diagram, there's definitely also, this is bending moment diagram. There's also what? There's also a shear force diagram, right? Shear force diagram. And shear force will, if you cut a cross section, it'll cause what type of stress? Shear stress. Okay, we call that the bending shear stress in this case. Okay? Yeah. Then why don't we consider that then, right? So this is basically one of the conclusions, if you recall, that I told you. The bending shear stress has a maximum at the which location? At the neutral axis location. And we had an example previously, and that example actually showed you the shear stress caused by the bending, the shear force are not as critical as the normal stress caused by the bending normal stress, right? And this is basically commonly true for shaft design. So that's why when you cut a cross section here, okay, you don't need to look at the neutral axis location. You only need to consider the top or the bottom, the critical location. Okay? Yeah. So having this clear as to where you want to look at it, what type of stress you want to look at it, and now we can jump into this question and here basically to nail the answer, right? Yeah. So first we can find the key F. Okay, finding the key F meaning we had to find. Okay, so key F is 1 plus Q KT minus 1 because there is bending moment, there's no torque, so that's why we're only looking at the Q, not the Q shear, right? Finding this formula basically meaning what's the Q and also the KT, right? So you need to find these two at here. Now, finding the KT, basically you had to find the right appendices from A-15 in order to find the KT. So do have a little bit of time, right? Where is the here? So this is a diagram to find this KT value. So you look at this diagram here. This is exactly match the current question, right? You have a stepped shoulder, you have a fillet radius, and you have a bending, constant bending applied. Okay, and there's a rotating shaft. Okay, so this is a figure A-15-9. So this is basically you need to look at the figure A-15-9 to find the KT. Okay. So this one you can get the KT is approximately 1.65. Okay. So basically find the R over D, radius over small d. Okay. And also capital D over small d, and then you can find the KT value. Okay. To find a Q here, you can use the formula we just derived, we just provided. So this is the formula for Q, and then for the root A at here, this is essentially to use which now? Now, because this question, if you look at the question, everything is given in millimeter. It's a standard unit. To find the Newberg constant, that's the formula, modified formula we had to use. Okay, so I had to use this modified formula to find the Newberg constant at here. Once you find the QA square root of A, then you can find basically you find that use the modified to find this one, which is 0.313, and the unit of this is millimeter. Okay, yeah. So now you can find the Q, which is 0.847. So these two together, you can find your KF. It's approximately 1.55. Okay. Yeah. So I'll finish this example in the next lecture, but take a look at the lecture notes. Okay, I'm going to also have an Excel file uploaded. This Excel file, as you're going to see, it actually helps you in terms of the calculation. For example, the Newberg constant, right? Okay. Yeah. So I'll finish example in the next lecture. By the way, assignment number 2 is posted, and it's due this Friday. I have assignment number 4, probably number 3, posted this Friday. So 1, 2, 3 will be the midterm coverage. Okay. Yeah. Thank you. Okay. Yeah, good.